Perfect, thanks. So yeah, so our next speaker is Thomas here, talking about prospects of a statistical detection of 21 centimeter forest. Thomas, over to you. It's 12 plus 3. I'll let you know when 12 minutes is done.
Okay, great. Thank you very much. Hello, everyone. And thank you, organizers, for giving me the opportunity to present our work on the 21 centimeter forest signal from the epoch of reionization. So this talk is heavily based on our recently published paper, so please have a look at it. Nitya Dan has, I guess, touched a bit on this topic of the 21 centimeter forest signal, but let me describe it in slightly more detail. So it's a series of absorption features in the spectra of distant radio loud point-like sources arising from the intervening neutral hydrogen structures. As you can see here in this animation in the bottom panel, you see the absorption features and how they correspond to the cold, neutral, and somewhat overdense IgM, intergalactic medium structures. So 21 centimeter forest is complementary to other 21 centimeter line observables. The main reason is, like I said, you see the signal in the spectra of this point-like, very bright sources, as opposed to the other 21 centimeter line observables for which you use CMB as your radio background. And hence this signal is subject to different systematics. It should be in principle less complicated to detect, but it has its own challenges, like the abundance of radio bright sources at high redshifts. It is complementary to the Lyman alpha forest as well, because it has a potential to be a unique probe of cold and neutral IgM at high redshift, as opposed to the Lyman alpha forest. And it has been suggested that it can be used to constrain, for example, nature of dark matter or supermassive black hole growth models, and so on and so on. So hopefully I have persuaded you that it is worth spending our time and effort to study this signal. So let's discuss why now may be the right time to try and detect it. So firstly, recent Lyman alpha observation seem to require ionization to be completed rather late, at redshift less than 5.6 around. In this scenario of this late ionization, we expect large islands of neutral hydrogen to be present at redshift as low as 6. And if you have that, and if these regions are cold enough, there is a possibility of detecting strong 21 centimeter forest absorbers, which would be great to do at redshift 6. Another improvement on the observational front in the field is the number of radio loud quasars identified at the redshift higher than 5.5 has more than tripled since 2020. Now we have around 34 good targets for the 21 centimeter forest observations and to point our radio telescopes at. Speaking of radio telescopes, the sensitivity of radio observatories is improving. So here I shown a plot of sensitivity as a function of a frequency at which we observe. So please focus on this red strip there. So that indicates the frequencies relevant for the 21 centimeter forest observations. And you can see that at these frequencies, UGMRT has a better sensitivity than LOFAR, for example. So from the currently operational facilities, UGMRT might be the best bet for detecting 21 centimeter forest signal. Of course, in the future, SK1 low will have a significantly better sensitivity, so the future looks encouraging. Okay, so let's discuss what might be a good strategy to try and detect 21 centimeter forest signal. I will discuss a statistical detection of this signal, and in particular, I picked 1D power spectrum of 21 centimeter forest. So here is an example of a synthetic simulated 1D power spectrum in orange. So this is based on 21 centimeter fast simulations. This is at redshift 6, and if we compare it with some noise limits, so if we assume that we point our radio telescope at one of the brightest blazars at redshift around 6 with UGMRT or 500 hours, you get this pink curve, the upper one. If we consider SK1 low observing over 50 hours, you get the other pink curve. And you can see that in this case, the signal at large scales or small k is above this noise limit. So there is a chance of detecting the signal. So this is encouraging. Of course, the signal itself will depend on the thermal and ionization state of the IgM. So in our modeling framework, so these two things, these properties are dictated by this fx. So that's the X-ray background radiation efficiency, and the XH1 is the mean neutral hydrogen fraction. So we can tweak these two parameters in our simulations, and this is what we did. So we ran quite a few models, simulations, and so we fed them into MCMC, assuming mock observation of 10 spectra at redshift 6 with a bandwidth of around 22 megahertz. And so this plot is one of the outputs that we get from our Bayesian statistical method. So here we assume observation by ASK1 low with 50 hours per source. So let me explain this plot. The crosses correspond to the true values that were assumed for the mock observations, while the shaded regions with corresponding colors indicate the posterior distributions from our analysis. And you can see that we are doing differently well at different places in the parameter space, naturally, because different places you will have differently strong or weak signal. But you can see that if we get a detection, we might be able to constrain both of these parameters dictating the thermal and ionization state of the IGM at redshift 6, which would be great. But of course, what can happen is that, okay, we do this observation and we don't detect the signal. We get a null detection. Do not despair. What we suggest is that null detection can be used to disfavor some of the regions in the parameter space, particularly the ones given by below the solid black curve, effectively putting lower limits on fx and upper limits on xh1. So just to compare it with some xh1 measurements from the Lehman alpha forest that we currently have, you see that we might be doing, in some cases, even better than what we currently have with these kind of null detection constraints from 21 centimeter forest signal. FX is still largely unconstrained, so putting any kind of constraints would be very valuable for in the community, I think. So, and just for a comparison, I also showed the same plot for UGMRT with 500 hours per source. You see that the constraints are not as tight as one would expect, but you know, you can still do some, you can still get some interesting results. So motivated by these results, we have submitted a proposal for the observations by the UGMRT to target two brightest radio loud quasars at redshift around 6 with the aim of statistical detection of the 21 centimeter forest signal. In particular, we asked for 147 hours in total to be split between those two sources. And what we claimed is that if we get this observation, if we acquire this and we combine it with archival data that is already available on one of these sources from UGMRT, we can achieve noise RMS of around 2.7%, which is a couple of times stronger noise than what I showed you in the previous plots or slides. But in this plot, you see that the signal can be still above the noise limit. So there is still some chance of getting the detection. Unfortunately, our proposal got rejected. However, all of the referees' comments were constructive, and we are thankful for them. For example, they agreed that we did not really persuade them that with these kind of observations, we will be able to achieve such a sensitivity or noise level. And I agree that our analysis can be improved in this direction. For example, we did not really consider any effect of RFI. Indeed, yeah, so we took their suggestion seriously, and we started looking into analyzing the archival data from UGMRT on one of these sources with the aim of better understanding the instrumental features and developing techniques for improve the parameter inference and noise mitigation. Okay, but I will repeat myself, but I really want to emphasize that a null detection would be still valuable because we can translate it into first of a kind constraint on the thermal state of the cold and neutral IgM at redshift 6. And I believe that this is worth pursuing further, and we will do so. Sorry, we will do so. Okay, so, and like I said, we are developing different methods for improving our analysis, for example, parameter inference, and in particular, we're employing machine learning methods. So here I showed the same plot I showed you before for UGMRT 500 hours per source. So this is based on Bayesian statistical methods. But we are also working, these are preliminary results. This is led by Samir Patil in collaboration with Suman, Matra, and Girish Kulkarni. And for example, what we are doing is we take the flux spectrum of 21 centimeter forest signal instead of 1D power spectrum. We use this, we train the denoising autoencoder based on the convolutional neural network. And we combine it with the XGBoost to get the mapping and this way we can get some parameter inference. And just to give you an example, some results of this method. So this is the plot, and you can clearly see that getting the posterior distributions from this method are more accurate, especially in the places where we expect signal to be weak, for example, at low XH. 1. So I guess this is a very promising way to go further. And yeah, just to sum up my talk, I hope I have persuaded you that prospects of detecting the 21 centimeter forest signal are improving on instrumentational, theoretical, and observational fronts. 21 centimeter forest is a unique probe of our universe, especially of the cold and neutral IgM at high redshift. And we believe that we can put constraints on the thermal and ionization state of this IgM, even in the case of a null detection of the signal. And currently we're improving our analysis. One way is that we are utilizing the archival data from the UGMRT, and we are employing machine learning techniques. So thank you for your attention.
Thanks, Thomas, for sticking exactly to 12 minutes. We have questions.
Cool.
Yeah.
Amazing.
Always seem to be the first one asking questions. Thanks, Tomáš. Very nice talk. I think we spoke last year as well and asked you a question about the mode mixing. If you look at these point sources, you're effectively, of course, averaging over short up to very long baselines. Now we know, right, in the power spectra, the 2D power spectra, that you have this wedge, of course, you're going up to very high delays. So if you put that in an image and then look along the line of sight, you'll get all these spectral fluctuations due to all the side lobes of all the other sources. So you need to either go to the very short baselines or at least cut off the baselines at the point that this doesn't sort of mix into your 21 centimeter forest. So have you looked further into that effect to see whether it's not sort of a showstopper?
I believe that there is Nityanandan has looked into that in his paper from 2020, I believe, if I'm not mistaken. But yeah, we did not look into this. I'm sorry. But yes, this is definitely one of the things that we should check, besides, other things that we find when we found already when we started looking at the the actual real observations at these frequencies. So
I think the archival data will tell you, right?
Yes. Well, that's what I'm saying. That yeah, well, I mean, we started looking into this archival data, and yeah, I mean, we just need to work more on this to see, for example, to look at this effect as well.
Thank you.
Yeah, just wanted to comment on Leon's question. Yes, there is a mode mixing effect. I did some estimate of it, and it's not a showstopper. It's very similar to the wedge kind of thing, and there are modes which are relatively free, even along that 1D power spectrum. I had a very quick question. These two targets, do you know what the radio strength of these targets are?
So one of them is at, so first of all, one of them is at the redshift 5.8, and that has around 110 millijansky at, I don't know, like 147 megahertz or something like that, I think. I think it will be less at like 200 megahertz, which are the relevant frequencies for 21 centimeter forest. And the other one, the Blazer at the redshift 6.1 is 64.2 millijansky at 147 megahertz. So those are the two brightest ones.
Cool. Yeah, sounds exciting.
Yeah, but maybe just to add a note on that, there's a couple more that have like above 10 millijansky at high redshift. So,
any further questions? I had a very quick one, Thomas. When you were trying to do the parameter inference in the first few slides, where you're constraining fx and xh1, there seems to be a bimodality in the solutions in one of the cases where it was preferring a combination of two different fx and xh1 values. If you could go to that slide.
Maybe I can go.
Yeah.
Yeah, this one.
Right. So the fx of -3 and a very low value of xh1, but it also prefers a fairly high value of xh1 there. So is there a physical understanding of why these kinds of multiple solutions would exist?
So maybe I can show you two plots how the signal behaves when we change these parameters. Yes, here we go. So this is the mean, or actual median, I think, 1D power spectrum over 1,000 lines of sight. And so we fix xh1 here to the value given in the plot, and we vary the fx. So that's one way how the signal can vary. And if we do the same thing, but we swap the parameters, so if we fix fx and change xh1, this is how it behaves. So they can, to some extent, they can behave similarly, because if you have low xh1, you have larger or more ionized bubbles, so you completely eliminate the 21 centimeter forest absorption features. If you have high fx, you will have warmer IgM in the neutral regions. That means that the signal will be suppressed. If it's suppressed too much, then you just don't see the signal. But they also behave somewhat differently, exactly because of the same reasons. If you change xh1 or you have more ionized bubbles, you completely eliminate the features, while with higher fx you suppress them. So that is my understanding, at least.
Thank you. If we don't have any further question, let's thank Thomas once again.
Thank you very much.